Hi there. Today we're looking at fast reinforcement learning with generalized policy updates by Andre Barreto, Xiaobo Hou, Diana Borsa, David Silver, and Doina Prekub. So on high level, this paper proposes a framework for reinforcement learning where you have many tasks at the same time. And they propose a framework where they learn many policies at the same time that can or cannot correspond to these tasks. And then their argument is that if you now have a new task that you haven't seen before, you can easily construct a solution to that task from your old policies, basically mixing what you learned about your old tasks. And it's a pretty general framework, and we're going to look at it. In my opinion, it's pretty cool for certain settings. However, I think it kind of breaks down the more general you go, which I guess is expected of such a framework. But it's, as you can see, it's kind of math heavy, but we'll get into the examples and what it's potentially useful for. All right, so that was it on a high level. If you like content like this, don't hesitate to subscribe to the channel and share it out. Leave a like and tell me in the comments what you think. I'm still reading all of them, so I will see it. Cool, let's dive in. So they say the combination of reinforcement learning with deep learning is a promising approach to tackle important sequential decision-making problems that are currently intractable. Well, they're talking about, things like mostly these game-playing AIs like Go and things like this. So where this combination of deep learning with reinforcement learning has really shined, or shone, whatever. One obstacle to overcome is the amount of data needed by learning systems of this type. So again, if you look at these systems like AlphaGo, they need a simulator and they need to collect enormous amounts of data. Even more so with systems like the Dota AI, the OpenAI 5 Dota, or StarCraft playing Alpha Star. I think it's Alpha Star. They need so many simulations in order to learn about the tasks because they always start from scratch. In this article, they say, we propose to address this issue through a divide and conquer approach. We argue that complex decision problems can be naturally decomposed into multiple tasks that unfold in sequence or in parallel. By associating each task with a reward function, this problem decomposition can be seamlessly accommodated within the standard reinforcement learning formalism. Okay, so what are they saying right here? They are basically saying that if you have a task, let's say you want to get from here to here, and that's very complicated. Let's make it complicated, super duper complicated. You can basically subdivide that task into multiple subtasks, right? So here is like left turn, right turn, go straight, left turn, go straight, right turn, and so on. And each of these subtasks, you can see the two right turns here, might share a lot of common information. There could also be tasks that are at the same time, like you need to go forward and jump, can be decomposed into going forward and to jump. Now what they're saying is if each of these tasks now has its separate reward function in the environment, like for some reason the environment tells you this, by the way, is task 1, and you're going to get a positive reward if you do a right turn. And this down here is task 2, the left turn task, and you're going to get a positive reward for that task. So the entire task state can be decomposed into a vector. So in our case here, we have maybe a vector with 3 elements, okay? The 3 elements correspond to turn right, go straight, and turn left. And now this right here is your reward vector. So we're no longer in this framework, we're no longer talking about just a reward, we're talking about a reward vector. Now, each of these tasks is going to give you its own individual reward. So let's say you're here and you're actually turning right. This is going to give you a reward of 1 for this task, but rewards of 0 for the other task. Okay, so the environment will somehow tell you which tasks you get reward for. Now, there is a notion where you can map this back to a single number, and that is the second thing they introduce here. So the second thing they introduce here is this thing they call W. So W is going to be a mixing vector. W is going to be a vector. I will call W right here. This is the reward vector. W is going to be the vector that tells you your final reward. So here we're going to do an inner product. So we're going to transpose this and multiply by W. And W mixes these rewards and comes up with your final reward right here. So this is maybe the reward vector. This is the reward number. How are we going to call this? Reward number. So in this case, W would have to look something like this, let's say. This is an example. So the task right here would be to only do right turns. Now, this is not a really nice example. We're going to see some nicer examples later on, but you can see that now the environment is specified as a vector of rewards, and you can create a specific tasks like turning right simply by adjusting how you mix these different things by this vector W. And this is going to be the key ingredient here. So they discuss your general reinforcement learning lingo, and I think we've gone through this a number of times just very, very quickly. In reinforcement learning, you're given these transitions. You are in a state, you take an action, and that leads you to get a reward, R prime, and you get into a state S prime in the next state. They say the reward is given by the reward function, so the reward is purely a function of where you are and what you do and where you get to. Now, in most reinforcement learning problems, you can actually kind of forget about this part right here because, well, it is kind of important, but you could, most reinforcement learning problems, the reward is simply a matter of where you are and what you do. And this can be a random variable, there can be randomness, but maybe it's easier if you, for now, think about the reward simply as a function of these two things. So what you want to discover is a policy pi, where you input where you are, and the output is going to be what should you do in that situation. Okay, that is a policy. And associated with each policy is this thing called a Q function. So you can see right here, the Q function of a policy is going to be a function of where you are and what you do. And this is a bit confusing, but it basically means that you are in state S. So you are here, and you have, let's say, 3 options: action 1, action 2, action 3 to do. Now the Q function tells you, the Q function, this is S, and the A's are the numbers, okay? So let's say we plug in the state S, and for A we plug in number 2. What it will tell you is, if I am in state S, and I perform action number 2, then how valuable is that for me? And value is defined by all the reward that I'm going to pick up from now until the end of time. Or the end of the episode, it depends. But let's say until the end of time. Well, how much reward am I going to pick up from now until the end of time is a bit of a vague, not a vague question, but a difficult question. I can tell you how much, I could estimate how much reward I'm going to pick up in the next step because I know what action I'm doing. I'm performing action number 2. But what happens after that? Who knows? So that's where this policy right here comes in. This policy right here says, so the full definition of the Q function is, if I'm in state S and I perform action A right now, and after that I follow policy pi, what is my reward going to be? Well, now it's well defined. So right now you do action A, and after that you do whatever action the policy tells you in that specific situation. Okay, so that's the Q function. And you can pretty easily see that if you have a Q function, right, if you have an accurate Q function, you can get a good policy by simply always going with the action that gives you the highest Q value. Because it's because of a recurrence relationship called the Bellman equation. This thing right here. So your Q function basically decomposes into the reward in the next step, as we said, plus whatever happens after that. And whatever happens after that is just by the nature of how the things are defined, is going to be the Q function of whatever the policy is telling you. So you can get a pretty good policy by always doing whatever action your Q function tells you is best. This step of calculating the Q function is called a policy evaluation. And this paper here is going to generalize these notions. So this is a policy evaluation, and then the act of selecting an action is going to be a policy improvement. These are just names, okay, but we need to know them because the paper introduces two new things. I'm going to, where do I highlight policy evaluation? I don't know, but here they say this is the policy improvement, okay? Here, policy evaluation, policy improvement. These are the two steps. So the first step is calculate the Q function. The second step is to select an action. And you can see how these things interlock, namely, we can calculate the Q function of a given policy, and we can improve that policy by selecting whatever action is best for the Q function. This paper generalizes this, and you can see that there is a little R right here. So the R is just a specific way to reference the reward function used right here, okay? And you can see it here as well. Now, usually we have one policy and one reward, right? And so what we do is we improve the policy, and that leads us to better evaluate the Q function for a given reward function, and that leads us to improve the policy. Now this paper is going to transform this into the following. We have many policies. So we have policy 1, policy 2, and so on until policy, I don't know, P. And we also have many reward functions. Reward 1, reward 2, reward 3, and so on until reward, let's call that R. So we have many different tasks right here, and we have many policies. Now, in essence, they don't need to have anything to do with each other for the theory of this paper, but I can simplify this a bit of how they see the world. So let's say you have an agent, and the agent has been trained on simply that first task right here, and has been trained using classic Q learning, reinforcement learning, whatnot, and that results in this particular policy. And then the agent, just from scratch, you restart it again, you run reinforcement learning just on reward number 2 and obtained policy number 2, and so on. So you do this for all these rewards individually. Okay, so you give the agent a new task and you ask it to learn a policy for that task. Now you're in a situation where if you have a new task, so R new, the question is, do you again need to train a new policy? And the answer for this paper is no. Because we have all these policies, we don't need to train anew. We can simply mix and match these policies that we already know to obtain a good solution for the new task. So how does the paper do it? It does it in the following. It defines the successor features. Okay. Maybe it's better if we first go to an example. So the example they give here is the following. Otherwise, I guess this might sound just a bit too abstract. Okay, so you have this world here. The agent is the thing here in yellow, and it can just move. So its actions are move left, up, right, down. This is one step. Okay. In the environment, there are two different objects. One object is a triangle and one object is a square. Okay. So there are a number of tasks we can define right now in this thing. So we define tasks according to a reward function. So the reward, let's say the reward 1 is going to be 1 if it picks up a square, the square, and 0 else. Just if it picks up a square on any given step, we give it a reward of 1. We don't care about the blue triangles, okay? And then reward 2 is going to be the opposite. It's going to be 1, not the opposite, but 1 if it picks up a triangle, and 0 else. So you can see the good policies right here. So pi 1 is a good policy for reward 1 because it just goes and collects these red things, doesn't care about the blue things, just goes and collects them. Pi 2, it goes and collects the blue things, doesn't care about the red things, okay? So let's imagine that you have run reinforcement learning twice, once for reward 1 and once for reward 2. And now you have two policies, okay? So you have two policies. This will lead to pi 1, this will lead to pi 2. And now I give you the third task. Now the third task is a bit special. It's 1 if you pick up a square, and it's 0 else, except it's -1 if you pick up a blue thing. Well, the order of these is kind of wrong, but it's just for visual representation. Okay, so now you're asked to pick up the red things, but avoid the blue things. Okay, pick up as many red things as you can, avoid the blue things. And again, as we said, the question is, do you now have to run reinforcement learning again in this agent with your simulator using like Q-learning or something like this from the start? Or can you come up with a solution just given these two policies that will perform well on this new task? Okay? And we're going to see how they do it. So what they do is they use successor features. So these successor features, I've done a video about successor features, and I'll link to that. You can look at that, but essentially, these successor features are defined like this, and for that we need to know what this thing is right here. They simply call this a feature function. Okay, it's very ambiguous term. A feature function is a function that takes in a transition, so state, action, next state, and maps it to a high dimensional vector. Note this is almost the same as a reward function, except the reward function simply maps it to a number. Now this is mapped to a higher dimensional thing. Again, I kind of wanna leave out the next state right here just to make things easier on you. So a feature here can be many things, but the structure of the features is going to be such that the reward function is going to be this feature times this W vector. So I was a bit not correct before when I said the reward is now a vector. The reward of a particular task, W, can be seen as the inner product between the features and the task vector. So W specifies the task, and the features, well, they specify the features. In our case, it can be fairly simple. Namely, yes, I was definitely wrong at the beginning. So the feature functions right here is which object do you pick up, okay? So we define the feature function as 1, 0 if you pick up a square, and we define the feature function as 0, 1 if you pick up a triangle. And now you can, and we define it as we define it as 0, 0 if you pick up nothing. And now you can fairly easily see that the reward of each task can be simply calculated by mixing the features accordingly. Okay, so reward 1 is going to be simply the feature times a 1, 0, which is the W vector. Okay. So I can specify a task by giving the appropriate W vector. And now you can see that if this is my reward function, my agent can go out into the world. If it collects a square, it is going to be rewarded right here. If it collects a triangle, even though the features indicate that it collected a triangle, it doesn't care about it because the W is 0 right here. If I now want to give it the new task, the same is true for R2, if I now want to give it the new task, R3, right? And you remember the reward function right there, I can achieve that reward function by simply multiplying the same features, the exact same feature functions, by this vector right here. Okay? Remember, there is a slight difference between the reward function and the feature function in this particular example. The idea of the paper is that the feature function can be rich in expressivity and, you know, tell you all sorts of things about your current state, and the reward function is just a number, right? And then the reward is specified by simply linearly mixing these features. So the structure imposed by the paper here is that there are such a thing as a feature, and any task can be described by mixing these same features. Okay, that's the issue right here. So the features are going to be constant across tasks, whereas the W defines the task. All right, so the goal here is that if you have learned many things during your tasks, what you want to do is you want to learn this feature representation that is the same across all tasks, and then you want to simply have the W specify how to mix these features to get the reward. Now, of course, this is a very strict, very definition. Not a lot of things will fall into this unless you make the features like exponentially big, of course. However, they do discuss whenever a task doesn't fall into that. So I hope you're with me so far. This is the first kind of restriction we impose on our worlds that we can tackle with this framework, namely that all of our tasks in this world have to be a linear mix of the same features. If that's given, then then we can derive policies for tasks that we have never seen. We can derive good policies by doing zero learning. Simply by specifying the task, we can have a good policy for that task from the policies we've already learned for the other tasks. Okay, so the reward 3 is now simply this. And yeah, notice it's not the same as the reward function, because the reward function had 1 if you pick up the square, -1 if you pick up the triangle, and 0 else. So the 0 we don't have to specify here because it's not part of our features. All right, so you can see that the reward function is given simply by that. And we can now, as I said, derive a good policy for this reward by looking at the other policies, even though none of these policies has ever learned to avoid anything. So it defines these successor features right here. So the successor features is much like the Q function. You can see the signature is almost the same. So as a Q function tells you how much reward you're going to get if you do the action A and then follow policy pi. The successor features almost the same thing. However, it doesn't tell you what rewards you're going to get. It tells you which features you're going to get. And which features, by that we mean the sum of future features. Now you can see this a little bit this it of course it comes from the fact of the linearity up here, so it's not really an additional restriction, but it's simply to clarify what this means for your environment. Your environment has to be able to be looked at in terms of these features, and these features, they need to be cumulative. Again, that comes from the fact that it's linear, but to see. So a feature like I want an even number of steps or something like this would be terrible because, and they're going into things like this later, but it would be terrible because here you have the sum, and as soon as if you have a feature that is very high, if you have an even number of steps, then or if you have a feature that counts the steps, you will never be able to do well, because if you have a feature that counts the steps, it simply counts up and up and up and up, depending on how many steps you do, and your reward can never be specified in terms of a mix of these features, and therefore your successor features are going to be useless. But in our case, where feature 1 is is how many of the, sorry, I have to rephrase. Our feature 1 is whether or not you pick up a square. Therefore, if we sum it up, our successor feature 1 is going to be the number of, this is a pound sign, the number of squares that you pick up. Okay? Similarly, our feature 2 is whether or not you pick up a triangle in a particular step. So our successor feature number 2 is going to be the number of triangles that you pick up over time. You can see that the successor features is kind of the analogous of your Q function, but it is not in terms of a single number, the reward. It is going to be in terms of these features, which is an entire vector. Okay? And because we've constructed this in a linear way, you can also pretty clearly see that the Q function is inherently related to the successor features. You can obtain the Q function by simply multiplying these successor features by your task vector W. Now, a lot of you might be wondering, where does this W come from? And in our initial case, we're just going to frame everything as being given, right? So we're given this W. We're defining everything from our godlike perspective for now. So don't think all of this is learned by now. Yeah. All right. So how can you now derive this magical new policy? Okay. So let's say we have this policy 1 and we have the policy 2, and you have these features that you've learned constantly over both tasks. In fact, it's given, right? This pi function, we impose it that the feature 1 is whether you pick up a red square, feature 2 is whether you pick up a blue square. Then we know that the reward functions can be achieved by doing the W. So this here, your W is going to be 1, 0, and your W here is going to be 0, 1. And now we want a good policy for task 3, and we know we can achieve this by the -1 W. How can we derive a good policy? And this is this algorithm, this general policy evaluation, a general policy improvement. So it assumes that you, as we said, you have many different policy. So here you can see policy 1. Where's policy 2? Here's policy 2, and so on. It assumes that you have many different features and therefore many different successor features. In fact, you have a vector of them, right? So here you can see feature 1, feature 2, and so on. And it also assumes that you're in a current state and you have many actions at your disposal right now. Action 1, action 2, and so on. Okay, so this is all the past. You've already defined your features, you have learned these policies, and now you're given a new W new. In our case, it's this 1, -1, and we want the best action. So we are in state S, and we are given this W. We want the best action. Now here is a method where we can simply calculate the best action in terms, by not reinforcement learning at all in this new task. So by structuring things like this here, so what does it really say here? This thing says, we are going to evaluate all of these different cells of this tensor right here. So we're going to determine what is the successor feature number 2 for policy pi 1 in state S if I right now do A2. This is very abstract. So let's say you're here, and action 2 is actually going to the right. Okay, so you're here. Oh, this was yellow. It doesn't matter. So this is action 1. This is action 2. So action 2 is you go to the right. Okay, you can see that this will let you pick up a triangle. Now here, that's action 3, and so on. Okay, so what's this number going to be? So we are in state S, as we said, and we do action 2. So action 2 is going to pick up a triangle. The picking up of a triangle means that our pi for this step, or sorry, our phi for this step is going to be 0, 1. Okay, so our successor features, this is not the features itself, this is the successor features. The successor features decompose into the next step plus all the next steps that we can follow. Okay, so all the steps that will come. So what are these features going to be? It's going to be the sum over that plus everything that follows. And I can take a little bit of a guess here, which means that this number, so we only care about feature 2 right here, this feature 2, this number is going to be 1 for the next step because we are going to pick up a triangle if we do action 2. But then after that, we're going to follow policy 1. And policy 1 has been trained to pick up the red squares and not care about triangles. So I'm going to guess that every now and then it will kind of step over a triangle, but it won't explicitly go look for them. So let's say the episode was 10 more steps, but the board has like 100 squares. And it has like 3 triangles on it. So let's say that's like 3/10 in expectation. Okay, so this is going to be the number that we're looking for. We're doing this for every single one of these cells. Okay, this thing is going to do for every single one of these cells. And this is very similar to evaluating Q functions, except we're evaluating an entire vector right here. That's the difference to simply learning many Q functions. So if you were to evaluate only a Q function, then you would only have this first matrix, this first block right here. Okay, but you have feature 1, feature 2, and so on. So you calculate everything in terms of these features, and then by linearity, you can mix it with that vector. So in our case, this is going to be the 1, -1, which will give you the Q functions, right? From what we've seen before, you obtain a Q function by simply mixing your successor features with your with this task vector. And if you have a Q function, you can pretty easily determine which action you should take. Now you have here a Q function with respect to every single policy, but you can simply take the max, right? So the max across all of this will determine, so you take the max across all the policies, which will give you the Q function for a particular action over all policies that you consider. And then you can simply take the argmax of that and determine the action you should take. Okay, so it's a pretty big evaluation, but if you do this, that means you don't have to do reinforcement learning on this task. It simply determines which action right now is the best, given everything that I know from these old policies about the task. And that's not going to be like the optimal policy per se, but is going to be one policy that's pretty good. And you can actually prove some things across that. So they do this right here, and you can see that here is what Q-learning does on this new task of picking up the squares and avoiding the triangles. Q-learning takes a while to get there. However, if you do what they are suggesting, and you give the W, you can supply the W almost from the beginning. You see right here, almost from the beginning, it is at a high reward. Now, Q-learning surpasses it eventually, but it's pretty impressive that without doing any learning, you are immediately good, right? Now, the caveat here, of course, is that they already need these policy pi 1 and pi 2 given to the algorithm. And that comes from previous reinforcement learning trials. And they say that they give these trials as many steps as Q-learning uses. So they give them these amounts of steps on these other tasks. So the comparison here is a bit shaky, if you ask me. But the point made is that if you have a new task right now, you can obtain very good solutions and you don't have to do anything. Okay, and these solutions can be the basis for new reinforcement learning, right? You could start Q-learning off right here and then get here much faster potentially and so on. So the next objective right here is that now we have defined the tasks and we know what these features are, and we know how to mix these features as imposers of the task. So what happens if we only have the reward function? We specify the task only in terms of the reward functions, but we're kind of looking at the features and we're like, agent, please figure out yourself how to apply these features in order to make the reward high. And that's what this thing is right here. This GP and GPI with regress W. So you don't no longer tell it what the W is. It needs to infer it through reinforcement learning, right? So, and it's not really reinforcement learning, but what it does, where is it? Yeah, it simply, because all of this is linear and this thing here is given, so always remember, this thing here is given, and these are the rewards that you obtain. You can simply do a regression to figure out the W of the task. Now that's going to take some time, but as you can see right here, it is going to take a lot less time than doing Q-learning from scratch. Notably because you have good features. So this gets closer and closer to transfer learning, right? If you imagine that this right here is your pre-trained neural network, and you simply learn the last layer of it. You freeze this, you do transfer learning, fine-tune the last layer. Here we are. Right? So it gets closer and closer, and you'll see this trend right here. So it's pretty cool what you can do, but basically, I think it's a lot of math around a framework, and the more and more you relax the kind of impositions that they need for their framework, the more it gets back to simply, well, we do reinforcement learning, at least in my estimation. So before we look at that, this here is a pretty cool experiment where they look at how the different tasks can be achieved if you give different policies. So you'll have noticed that we have always given these two tasks 1, 0 and 0, 1, these were our tasks that we trained on, and then -1 is the task we evaluated on. Okay, and you might object and say, wait a minute, these two tasks, you know, they're pretty good as, let's say, pre-training tasks, because, and it's basically the standard basis, right? And any other task can be mixed from those. So these are orthogonal vectors in this vector space. So you're being pretty generous to this system. What happens if we're not as generous? So that's what they do here. So they have different policies, and they evaluate how much you can learn with these different policies. So the way you have to read this diagram is right here is going to be the 1, 0 axis, as they label it right here. And this is going to be the 0, 1 axis, and this is evaluation. So every direction on this circle defines a task. For example, this task right here, as you can see, is going to define the task of picking up both the squares and the triangles, right? Whatever you pick up, you get a reward. However, the task down here is going to be, please pick up the squares, but avoid the triangles at all cost. Okay, and now they're going to look what happens if we supply different policies to choose from. Remember, we're in this situation, we're again in this situation where we give everything, and we give initial policies, we give the task vector, and now it's about deriving a good policy just from looking at the old policy, so no learning. As a baseline, you have Q learning, which into a given direction tells you basically how long Q learning takes, or how far Q learning gets with a given amount of steps, indicated by this 1, 2, 3, 4, and so on. Yeah, you see, I think this is in how far Q learning gets with these amounts of steps is the dotted lines right here. So Q learning gets this far with 10 to the, I don't know, 4, and then this far 10 to the 5, and so on. So these are comparisons. You can see that on the outside, Q learning is going to beat these methods. But our hope is going to be that, of course, if we have this zero-shot generalization, it's much better than running Q learning for really long if we get close to it. So the green thing is what we've already seen. Policies 1 and 2 will give you a fairly, good, fairly good extent right here. So what does it mean? It means it can solve pretty much everything from here, this task, this task, this task. It kind of falls off once we go down here. So once we go to the avoid section, it sort of falls off because it has never learned to avoid. Now, still, we can, of course, do the avoidance by simply imposing a negative collection. But negative collecting and avoiding aren't exactly the same thing in these environments, right? Because avoiding can also be going really close to something but not hitting it, while collecting, it's not the inverse of collecting. The inverse of collecting would be like run away as far as possible. So we can expect that we've only ever learned to collect. We're not going to be super good at avoiding. Then the other extreme is when we give policies 3 and 4. Now, I haven't told you, but you can see it right here. Policy 3 is explicitly to collect one and avoid the other, while policy 4 is the opposite right here. Avoid the squares, collect the triangles. And now this policy should be pretty good on all of the tasks in between. As you can see, it has the biggest extent right here. And that also makes sense. By the way, there's nothing down here because the task of avoiding both things doesn't really make sense, because you can just stay where you are, because there are also these squares where there's nothing. But you can see that the mixture of those is quite potent. So already we can see, even though these span a basis, in fact an orthogonal basis, as much as these. Because of the nature of the features that we define for the task, they are not equivalent in mixing after. So we can be more generous, we can also be less generous if we only provide policy 5. And policy 5 is simply to pick up both objects. Then we're going to have a pretty hard time when it comes to avoiding things. So you can see it can do fairly well picking up the various things in a positive manner. But as soon as we cross this line into this horizontal line into where it's about avoiding a particular object, it's not the choices of actions we have from policy 5 aren't going to be super good at that. And they do another thing right here. So the left thing is where they say it's important which policies we provide. And the right thing, they want to say something like it's important, so they want to say if we provide more policies, that can be advantageous because we basically have more options to choose from. Okay, so now they start off with policy 4, and policy 4 is simply avoid the squares, collect the triangle. And you can see it performs fairly well over here, where it's all about avoiding the squares and collecting the triangles. As soon as you get into, collecting, or even here the opposite directions, it's pretty bad, right? That's the red thing. And now they add policy 2 to policy 4. So policy 2 is going to be also to collect the triangles, but to just neglect the squares. And that will also do a bit better. Why does it do better? Because it's better at collecting, because this policy here also needs to avoid, and this policy here doesn't care. So in the regimes where it's better to not care than to avoid, adding this policy, adding these options is going to be good. And you can see that there's a general expansion here as we add more policies. However, I want to point out that, for example, here this black thing, which should be technically superior to the blue thing because it contains, as you can see here, all the policies that the blue thing contains plus another policy. I don't know if my vision, but I'm pretty sure here the black thing is inside the blue thing. So that means there can also be a disadvantage to adding more policies right here, because maybe you have too much to choose from. And so right here, what we say is we add a policy that is all about collecting the squares. And it is actually decreasing the performance. The addition of this is decreasing the performance on tasks where you have to avoid the squares, which I'm not sure if that makes sense. Again, the opposite of collecting isn't avoiding, but I'm just pointing this out. And this isn't really mentioned in the paper. The paper simply says, see, we add policies, therefore we are getting better. I don't agree with this given these results, or maybe the plotting is bad. All right, so they say, okay, more policies better, which I disagree with. They also say, oh, we can, as much as we can regress the W, right? We regress W, we figure out the task. We can even learn the successor features, okay? We can, not the successor features, the pi functions that lead to the successor features. And you can see, if you do it with a true W, you're really good at the beginning. If you do it with a regress W, we can see that before, so this is the small version of this plot right here. This is like this section, I think, yeah. You improve. However, we can also learn this pi function. We can also learn the features. If we're not given the features, maybe we can learn the features. And they say, well, we can do this but also by regression. So here, what we can do is we can find the function that minimizes the function and the W along with it that minimizes this error right here. Okay, so you're finding the function and the W that matches this error. And this now really is like learning a neural network. I mean, you know, so I get it. You have the I here and the W doesn't depend on the I and so on. But you're getting more and more back to actually simply learning nonlinear functions, mixing them linearly right here. And I think that's going to be kind of the crux of this method, the fact that the more complicated your problems are, the less you are going to be able to do this kind of stuff. And they even go as far as to say, well, what if, like before, the reward is actually something like whether or not you have collected an even number of triangles or squares. Then they say, well, you can simply not have a single W, but you can find a function W. And now the policy is a function of the function of W, and you can do potentially the same regression problem, but as you can see, it gets, so now you, this right here is going to be a function of the state, and so you can see that it more and more, it simply goes back to basically Q-learning again. The only difference here is that you have this intermediate features, but I think you can simply view this, let's say, as a hidden layer in a neural network. Now I get it, some are held constant across sums and so on, but you know, I like the method in terms of you know, in terms of the analysis. So if you are given all this stuff, it seems pretty cool that you can derive new policies. Its implication for lifelong learning, they say, look here, you have a bunch of tasks in your database that you've already learned on. Your agent is going out into the world. It faces a new task. It can use this thing. It can use this thing to obtain a new good policy for that task. It can then use reinforcement learning, RL, to refine that policy, and then it can simply save that policy into the database. So it keeps expanding and expanding this thing. So it keeps adding rows and rows and rows right here of new policies that it's learned over the course of its life. So once it's facing a new task, it can just kind of draw from its experience and derive a good initial solution. However, the actual analysis only works, I feel, in quite limited circumstances, and if you want to relax these limited circumstances, then you need to basically regress and regress and regress away from their setup. And I'm not sure. I'm not sure where this is going to go. If this is going to be a general framework for people, it seems like it because it's pretty easy. But then also it seems like most of the world doesn't really fall into this category. In fact, this divide and conquer approach, I'm not sure, but from divide and conquer, I almost imagine something like you subdivide and subdivide and subdivide until you are at some kind of basic task. They still only go for single tasks like this. Here the tasks are somehow in sequence, and I think we should really think about hierarchical RL. Now this can be a good first step right here, but most hierarchical RL, even the ones that specify themselves as fully hierarchical, like we can do many layers, they rarely go above 2 layers or 3, like one meta layer and one actual layer, like this one right here. They rarely go further. Maybe they go 2 layers, but that's about it. I've seen very little in actual hierarchical or divide and conquer reinforcement learning, just because it's so hard to train. Yeah, all in all, cool paper, and if you want to get into the math a little bit, I think it's pretty easy math once you kind of set your goals on what it's actually meant to achieve. If you just read from the beginning, all of these reinforcement learning papers, it seems a bit like, why? Why are we doing this, right? You just, we define this, we define that, we define this, and you're a bit like, yeah, but why? So often it pays in these papers to go at the end to the examples and then come back to the theory, knowing what they want to achieve. All right, that was it for me. Long rant. I'll see you next time. Bye-bye.